Dear students, in this module you will be learning about the general characteristics of free radical reactions. Understand in how many ways free radicals react upon their generation. Know about the different types of free radical reactions. Analyze in detail free radical halogenation. Study the Hunds-Dicker reaction. How do radicals react? A reactive radical has a choice. It can either find another radical or combine to form a spin paired molecule or more than one spin paired molecule, or it can react with spin paired molecule to form a new radical. Both are possible, and in this module we shall take up some examples of all such possible reactions. A third alternative for a radicals is to decompose in a unimolecular reaction, giving rise to a new radical and a spin paired molecule. We can also see these possibilities of radical reactions into four categories. They are addition to an unsaturated bond, combination and disproportionation, and rearrangement. These processes lead to stable end product. Some general characteristics of free radical reactions. All reactions involving free radicals share some general characteristics which are stated below. These characteristics are some for both aliphatic and aromatic reactions which involve free radicals. Number 1. Reactions are fairly similar whether they are occurring in vapor or liquid phase, though solvation of free radicals in solution does cause some differences. They are largely unaffected by the presence of acids or bases or by changes in the polarity of the solvents, except that non-polar solvents may suppress the competing ionic reactions. They are initiated or accelerated by the typical free radical sources such as peroxides or by light. Their rates are decreased or the reactions are suppressed entirely by the substrates that scavenge the free radicals. For example, nitric oxide, molecular oxygen or benzoquinone. These substances are called as inhibitors. Addition reactions. Addition of HBr to alkenes follow a radical reaction. The first free radical addition reaction to be discovered was the anti-Markovnikov addition of HBr to alkenes in the presence of peroxides. Further, it was noticed that the impurities such as oxygen and peroxides greatly increase the amount of anti-Markovnikov addition product in comparison to the Markovnikov product. This reaction was studied by Kharash and Mayo, who depicted that in the presence of a peroxide initiator, hydrogen halide adds to alkene via an anti-Markovnikov addition. Free radical mechanism. The carbon radical intermediate will be more stable if the carbon having a lone electron is more substituted. For this reason, the halogen atom as a free radical gets attached to the less substituted carbon, that is the anti-Markovnikov addition. For example, 2-methylpropene reacts with HBr in presence of peroxide such as tertiary butoxide or tertiary butoxide regio specifically to produce an anti-Markovnikov product. As it is seen in the given structure, the product formed is anti-Markovnikov, wherein the halogen atom adds on to the carbon atom bearing more number of the hydrogen atoms. The anti-Markovnikov regiochemistry is achieved from the addition of bromine radical to the less substituted carbon atom of the alkene due to steric reasons. As a result, more substituted radical is formed as an intermediate. The mechanism involves the following steps. First, the initiation step. Here, a radical is formed by the cleavage of the homolytic bond of oxygen-oxygen leading to the formation of the two radical species. A radical species further reacts with the HBr, wherein the oxygen combines with hydrogen, producing a bromo radical. Propagation steps. Here, the bromo radical adds on to the carbon atom, producing a carbon radical which is more substituted. A more substituted radical by all means is more stable, and hence the formation is much faster and a stable product is formed. Once the bromo adds and a carbon radical is produced, the next step involves the cleavage of the HBr bond, wherein the hydrogen adds on to the carbon radical and the bromo radical is let free, leading to the formation of a halo product. Finally, the termination step. The bromine radical generated in the propagation step can further react with another 2-methylpropene molecule. The reaction is ended in the termination steps, where all the chain carrying radicals combine with other radicals, as can be seen in the figures. Bromo radicals can combine with the another bromo radical, forming a bromine molecule, or a bromo radical might lead to a formation of a di-bromo product, and the reaction goes to the termination. Addition of HBr and HI to the alkene system. In contrast to HBr, the acids HCl and HI do not undergo free radical addition to alkenes, even in the presence of peroxides. This is because the abstraction of hydrogen radical from HCl is highly endothermic, and addition of ido radical to the alkene is also highly endothermic, which cannot be achieved by the following reactions. Addition of thiols to alkenes. The energies of the sulfur hydrogen bond and carbon bromine bond in the halocarbons are rather close, and so both the steps of the propagation in the radical chain addition of thiols to olefin are expected to be exothermic. Indeed, the addition takes place in the presence of light, air or peroxides. The thiol radical, which is RS radical, combines with the CH2 double bond CH C6H5, leading to the formation of again a carbon radical which is more substituted and henceforth more stable. This benzylic radical which is formed reacts further with the another molecule, leading to the formation of a thiol molecule, and a radical is produced along with it. Addition of alkyl radicals to alkenes. Polymerization reactions of alkenes. Alkyl free radicals can add to alkenes, carbonyl groups or alkynes. Among these additions, addition to alkenes is most important. They help in polymerization of alkenes. Free radical polymerization. The most commonly used peroxide as initiator for the free radical polymerization of alkenes in the industry is tertiary butoxide. For example, the polymerization of ethene to produce polyethene uses tertiary butoxide peroxide as an initiator, which initiates number of the radicals which can combine with each other, leading to a long chain polymer product. The mechanism involves the chain initiation steps, which consist of formation of a tertiary butoxide radical from the butoxide peroxide and its attack on ethylene to give the beginning of a polymer chain as a free radical, as can be seen from the given structures. The propagation steps consist of the addition of alkyl radical at the end of a growing polymer to another molecule of ethylene to give a new alkyl radical at the end of a longer polymer. Polymerization is well depicted here in the given structure. The termination steps are usual radical-radical combination and disproportionation reactions as explained earlier. Free radical substitution in alkane. You are already aware that the reaction of halogens with unsaturated molecules, alkenes and alkynes, in dark to give the addition product resulting in a vicinal dihalide from alkenes and tetrahalides from alkynes. Another reaction that you have already studied is the reaction of alkanes with halogens in the presence of sunlight to form alkyl halides via a free radical substitution reaction. This reaction is done using a higher concentration of halogens and in strong photolytic conditions. But the reaction takes a different course when the halogen concentration is low and in the presence of a free radical initiator. It leads to a radical allylic halogenation. Let us study about this in detail. Radical allylic halogenation. In the event of low halogen concentration, alkenes containing allylic hydrogens undergo a substitution at allylic position rather than the addition at a double bond. The product obtained is an allylic halide. Halogen on carbon next to the double bond of the carbons is called as the allylic position, which is acquired through the radical chain mechanism as shown here. Now, what is the reason for the allylic hydrogen exhibiting substitution process? The dissociation energy values for carbon hydrogen bonds of different types of hydrogen atoms are as allylic hydrogen atom 88 kilocalories per mole, alkylic hydrogen atom 98 kilocalories per mole, and the vinylic hydrogen atom is 106 kilocalories per mole. Note that the values for the allylic carbon hydrogen bond is lower than the dissociation energies for the carbon hydrogen bonds at the vinylic or the alkylic positions. The reason for this is that the radical formed when the allylic hydrogen is removed is most stabilized by resonance. Hence, at a low halogen concentration, substitution at the allylic positions is favored over the competing reactions. Addition of double bond if favored if the concentration of halogens is high. Allylic bromination. The most common example of the free radical allylic substitution of alkanes is the halogenation of alkanes with bromine in N-bromosuccinamide. When more than one type of hydrogen atoms are present, then hydrogen atom is most preferentially removed, which is the most stable radical. Hydrogen atoms are never removed from the hydrogen carbon atoms, which are sp or sp2 hybridized, rather only from the sp3 hybridized carbon atoms. Of the sp3 hybridized carbon hydrogen bonds, if carbon is attached with the heteroatom, hydrogen can be easily removed from it. If there is no hydrogen attached to the carbon next to the heteroatom, then allylic or benzylic hydrogen is removed preferentially. If any case there is no allylic or benzylic hydrogens present in the molecule, then the order of reactivity of the hydrogen atoms will be tertiary, secondary and the primary. As can be seen here, ease of removal of the hydrogen is of the order from 1 to 9, 1 being the easiest of all and 9th being the hydrogens as shown in the given structure. In case of allylic or benzylic halogenation, free radical halogenation is commonly applied because the radical formed are most stable. In case of alkenes, they can react with bromine by either an electrophilic addition reaction to give 1,2 dibromoalkanes or by free radical substitution reaction giving 3 bromoalkenes as depicted below for the cyclopentene. 3-bromoalkene is an allylic product. Of these, the former reaction takes place in dark and latter in the presence of a strong light. N-bromosuccinamide is often called as NBS and is used as a reagent to carry out free radical bromination. This helps to keep the concentration of bromine low and hence reduce the competition by the electrophilic addition of bromine to give any 1,2-dibromoalkane, which would be a addition product as represented above, which will be the competing reaction for the allylic halogenation. In these reactions using N-bromosuccinimide in CCl4, it has been shown that bromine is actual halogenating agent. Bromine is generated in the manner when NBr bond of NBS is cleaved homolytically, bromine is generated. This bromo then abstracts an allylic hydrogen from an alkene, which is cyclopentene in the above example. The HBr thus formed reacts with NBS to produce a bromine molecule as represented in the mechanism. This bromine molecule reacts with the allylic radical formed earlier and new bromine atom is produced, which further repeats the entire process and the reaction proceeds towards the termination. It is important to note that in allylic halogenation, transpositioning of the double bond can easily occur due to the allyl radical stabilization leading to shifting of double bond and the radical position. This can be very well seen from the example of 4,4-dimethyl cyclopentene. As can be seen, in the presence of NBS and photochemical radiations, a radical at the allylic position is produced, which undergoes the resonance stabilization, and as a result the bromo product could be formed at the ortho position to the 2-methyl substituted carbon atom or to the meta position to the 2-methyl substituted carbon atoms, and this is what we see in both the products which are obtained in the given reaction: fluorination, chlorination and iodination. Radical allylic chlorination. Like bromination, chlorination at the allylic position of an alkene is achieved when low concentrations of chlorine are present. The reaction is carried out at high temperatures. High temperatures help to produce the chlorine radical by the cleavage of the chlorine bond. Industrial uses. Allylic chlorination has an important practical applications in industry. In the industrial scale, allylic chlorination of alkenes is done because chlorine is not very expensive. For example, 3-chloropropene is used in the synthesis of epoxy resin via radical allylic chlorination as shown in the given structure. In case of fluorination, the fluoro radical is so reactive that the reaction fluoro with the carbon hydrogen bond leading to the formation of HF and CF bond is so exothermic that free radical fluorination results in violent and uncontrollable explosions. As a result, it is not of much practical usage. As compared to bromination, although chlorination reactions can be done using elemental chlorine, but these reactions are difficult to control because the chlorine radical is more reactive than the bromo radical and hence less selective. The better chlorinating agents are thionyl chloride, which is SO2Cl2, and tertiary butoxide chloride. At the other extreme, free radical iodination of alkanes do not work well at all, as the hydrogen abstraction step is too endothermic for the reaction to further substantiate. Polar effects in halogenation. As already discussed, in the free radical reactions, there is always a tendency for the formation of the most stable radical, and accordingly the order of reactivity in the aliphatic hydrocarbons has been found to be tertiary, secondary and primary as discussed above. However, there is now increasing evidence that the addition to the radical stability, polar factors often play a role in deciding which hydrogen of the reactant is to be abstracted by the attacking radical. For example, the relative reactivities of various hydrogen atoms of N-butyl chloride in photochlorination is shown below. Here we can see relative reactivities of the alpha, beta, gamma and delta hydrogens is of the order of 1, 5.5, 17 and 8. In spite of the fact that all the three carbon atoms alpha, beta and gamma are secondary in nature, there is a striking difference in the reactivity of hydrogen atoms situated on them. Had the radical stability been the only factor, then hydrogen atoms of alpha carbon should be the most reactive, as chlorine atom is expected to stabilize the radical on this carbon. These experimental observations are explained in terms of the polar factors due to the electron withdrawing inductive effect of chlorine. The attacking chlorine radical is relatively electronegative, and so it prefers to approach the hydrogen atom which are far away from the electronegative chlorine substituent. Predictably, alpha and beta carbon atoms are chlorinated to a lesser extent than the gamma carbon atom. Another example of the operation of the polar effect is the chlorination of propionic acid. Chlorine atom attacks the primary carbon rather than the secondary carbon, even though the secondary radical would be conjugated with the carbonyl group. Apparently, the polar effect due to the electronegative carboxyl group overcomes the radical stabilization effect. Hunsdicker reaction. Hunsdicker reaction is an example of involving free radical intermediates to yield the alkyl halide. Reaction of silver in the oxidation state 1 salts of carboxylic acids with halogens give an unstable intermediates which readily form alkyl halides. In this reaction, homolysis of the carbon-carbon bond takes place and it follows the radical chain mechanism. As can be seen, the silver salt of the carboxylic acid in the presence of bromine in CCl4 leads to the formation of RBr, HBr and carbon dioxide. The Hunsdicker reaction is the organic reaction of silver salt of carboxylic acids with the halogens to yield organic halides. The reaction is named after Heinz Hunsdicker and Claire Hunsdicker. Mechanism of Hunsdicker reaction. It involves formation of organic radical intermediates. In the reaction, the silver salt of the carboxylic acid 1 reacts with the bromine to give acyl hypohalite intermediate. A diradical pair is formed after radical decarboxylation, which will quickly recombine to form the desired organic halide. The reaction is wide scope and gradually gives good yield of alkyl bromide. Although bromine is the most often used halogen, chlorine and iodine that also then used. The R group may be alkyl or aryl. There are several variations of the Hunsdicker reaction that are known, in which silver carboxylate is exchanged for thallium carboxylate. In others, the carboxylic acid is directly treated with the combination of lead tetraacetate and halide ions, chloride, bromide or iodide for that matter. Through the application of these reagents, carboxylic acids are easily converted into alkyl chlorides and alkyl iodides. Alternately, a mixture of carboxylic acid, mercuric oxide and bromine also works well, as shown here. The metal carboxylate in the presence of halogen is going to form Rx, CO2 and a metal halide. To summarize, radicals normally react in 4 ways. These processes lead to a stable end product. The addition of HBr to alkenes in an anti-Markovnikov fashion was probably the first free radical addition reaction to be discovered. Free radicals add to common unsaturated center, namely alkenes, carbonyl group and alkynes. Among these, addition to C double bond C is important. In free radical reactions, there is always a tendency for the formation of the most stable radical, and accordingly the order of reactivity in the aliphatic hydrocarbon has been found to be benzylic or allylic, tertiary, secondary and primary. Halogenation of alkanes with bromine or N-bromosuccinimide is best example of free radical reaction. This chain reaction is initiated by homolytic cleavage of bromine induced by light or heat. The propagation step consists of 2 atom abstraction reactions. The Hunsdicker reaction is the organic reaction of silver carboxylic acids with the halogens to give organic halides. It involves free radicals as intermediates.